So chapter 3 is about linear programming. You are still going to use your calculator in this chapter, but you're going to use it to do the graphs. Whether you choose to do the shading with the calculator is entirely up to you. Most people find it easier to do the shading by hand than to have the calculator do it for you. I will show you how to have the calculator do it, but you have to do the same work by hand you'd have to do anyway just to get the calculator to verify that what you thought was right. So it's probably better to be sure that you know how to do it by hand. So the first method we're going to look at is the graphical method. We're going to graph linear inequalities. The difference between linear programming in the sense that it's a system of linear equations that we solve by matrices is that in linear programming we're not talking about equations, we're talking about inequalities. And in an application situation, what we have is we have a set of inequalities where we're limited by, for example, maybe the amount of labor and the amount of materials to manufacture something. And yet we have a profit or a revenue function that we want to maximize. We want to be able to get the most profit out of what we've got. Or we might be trying to have a cost function and we're trying to minimize our costs. So a lot of realistic problems involve inequalities. And an example is that a factory can manufacture no more than 12 items of something on a particular shift, or a medical researcher must interview at least 100 patients to be sure that a new treatment for a disease is better than the old one. So we have linear inequalities of the form A times X plus B times Y equal to or less than C. Or you can replace the equal to or less than with equal to or greater than or less than or greater than instead of the equal to or less than. Those are used in a process called linear programming to optimize, which means to find either the maximum or the minimum value of a quantity for a given situation. Now, the linear inequalities do not have to be in two variables. You can do a system of three linear inequalities with three variables. In fact, there are instances, if you really pursue this in input-output models, where you'll have as many as five inequalities and 5 variables. We're not going to go that far because you can't solve more than a system of 2 linear equalities with 2 variables. You cannot solve those with graphical methods. You have to use something called the simplex method, and we don't really have sufficient time for you to be able to learn the simplex method and be able to apply it effectively and not shortchange other topics. So we're going to leave out the simplex method. We're not going to do simplex. So we won't have any systems where there's more than 2 variables. We're only going to deal with 2. And we're going to solve them graphically, but we'll use matrices to find the intersection points or the graph to find the intersection points. It'll be up to you which way you want to do it. So let's start with our first problem situation. As soon as we define, this is what we just said, that a linear inequality has 2 variables and it always looks like one of those situations. And the numbers A, B, and C are any real number, positive or negative, doesn't matter. Negative numbers will have their potential applications, but A and B can't both be 0. A could be 0 or B could be 0, but not both of them, because then you would have 2 variables that make no difference to the outcome, and that's not a realistic situation. So here's our first example, and we're going to start out just by graphing inequalities, a single inequality. We want to graph the linear inequality 2x minus 3y is equal to or less than 12. And what we'll do is we'll begin by plotting the x-intercept and the y-intercept of the linear equation, ignoring the fact that it's an inequality. And the solutions to the linear equation in this case will also solve the inequality because the inequality has an equal to or less than sign in it. So basically, we just want to graph the line 2x minus 3y is equal to 12. So the way that we're going to do that, and I'm going to switch over now and actually graph it with you because I don't want to leave you behind.
Are you playing this on integrity?
Yes. Yes. So you will have the option of filling in your notes. Since we're going to graph the linear inequality, we're first going to look at the equation that's related to it, which is 2x minus 3y is equal to 12, and we're going to find the x and y intercepts. If we find the x-intercept, we're going to let y be 0. And that gives us the point 60. We choose to find the intercepts because they're the easiest 2 points to find. And then we're going to do the same with the y-intercept, except we're going to let x be 0. And y is -4. So we have 2 points, 6, 0, and 0, -4. So we're going to graph that equation first of all. So there's my x-axis. There's my y-axis. And you'll find that I don't always center my x and y-axis because you don't necessarily always have to. And in a realistic situation, we're really only going to be using the first quadrant in a lot of these problems. But we can plot the points here, 6, 0, 1, 2, 3, 4, 5, 6. So there's 6, 0. And 0, -4. 1, 2, 3, 4. And then because this inequality is equal to or less than, then any line that I draw will contain solutions to the inequality. So the line is actually going to be part of the solution. So that's the name of the line. And now comes the part where you have to decide what the rest of the solution is. So for the rest of the solution, I need to determine whether the solutions are this part of the graph or they're this part of the graph. So looking at equal to or less than, I need to pick a test value, a test point, x, y, and plug into that inequality and see if that test point works. Now the easiest test point to choose, if it's not on the line, is 0, 0. Because substituting in 0 leads to fewer arithmetic mistakes. So our test point is going to be 0, 0. So we say, is 2 times 0 minus 3 times 0 equal to or less than 12? Well, 2 times 0 is 0, 3 times 0 is 0, and 0 minus 0 is 0. Is 0 equal to or less than 12? Yes. That is a solution. Therefore, because that one is a solution, everything on this side of that line, every single point, is a solution. And if you want to verify that, then you can pick any other point that you want to. And I'm going to be lazy. I'm going to pick the point 1, 1. right here.
Okay, so from the point that you tested, if that point does not work. and
You
it's
go the
not
other
on-
way.
and it's
We
not-
would have shaded this way,
Okay.
okay?
But
So
if
it's
it
a,
doesn't-
it's a yes or no question. If your test point worked, go from the line toward that point. If the test point did not work and your answer is no, then don't go toward that point, go to the other side of the line. But I can verify this is correctly shaded because if I plug in 1, 1, then I have 2 times 1 minus 3 times 1 is equal to or less than 12. And that is 2 minus 3, which is -1, equal to or less than 12. And yes, of course it is. So I just verified that this is the correct direction to shade. You don't have to verify that. I could pick any point over here that I wanted to, and all of them should work. But if I were to pick, for example, 6, -1, right there. When we try 6, -1, we're saying 2 times 6 minus 3 times -1 is equal to or less than 12. Well, 2 times 6 is 12. -3 times -1 is +3, which is 15, and 15 is not less than 12. So that one didn't work, and no point on this side of the line will work. So this is our solution. This green area, all of that green area that's on that side of the line, or everything basically above the line, is the solution. Okay? So that means in order to actually write the solution to these problems that we're going to be doing, you're going to have to actually draw the graph and shade it, because the shading is the solution. Okay? Is everybody good so far? Any questions? Making sense? Okay. Let's try another one. X minus 4y is greater than 4. Again, we're going to start by graphing x minus 4y equals 4. So we're going to find the x-intercept. X minus 4 times 0 equals 4. X equals 4. So we have the point 4, 0. And then the y-intercept, we're going to let x be 0. 0 minus 4y equals 4. Y equals 4 over -4, which is -1. So we will plot those 2 points. Zero, -1, and 4, 0. And this time we're not going to shade in the line with a solid line, because this doesn't include equality. So when you have either greater than or less than without an equal sign, then when you graph your line, you're going to graph it with dashes, because the line actually is not part of the solution. It's just a boundary. I'm sorry, that's supposed to say equals because that's just our boundary line. Okay? Then we're going to do the same thing we did before. We're going to choose a test point. And again, since 0, 0 isn't on the line, it's okay to pick 0, 0 because it's easy. So we're going to test by saying, is 0 minus 4 times 0 greater than 4? 0 minus 0 is 0. Is 0 greater than 4? And the answer is no. Agreed? So that's not part of the solution. And since that's not part of the solution, then we're going to shade away from there. We're going to go to the other side or below the line. So here's our solution. And notice it does not include the boundary line. It goes all the way up to it, but doesn't include it. So that's the solution to x minus 4y is less than 4. Only points that are below the line. Question?
Because
There's no equal. On the first problem that we did, we had equal to or less than.
Oh, okay.
Okay? And even if we had equal to or greater than, the fact that we have an equal,
The greater than, the equal.
yeah, it's the equal that makes it solid. If you don't have the equal, if you just have less than or greater than, then you make it dashed. Okay? Making sense so far?
why'd you flip the sign?
I
Your
didn't.
solution?
Oh, sorry. I shouldn't have. Always ask. I'm glad you'll ask.
Well,
Yeah.
yeah, because I was like, I was like.
Now, why did you do that? Yeah, I shouldn't have. I just copied it wrong.
Okay.
But again, the solution is the shaded area. There's not a way to write it as ordered pairs or anything like that, or other than x is less than or y is less than thing. You've got to actually shade the area on the graph. So you're going to do some graphing this time. Okay? Now, this one is your turn. Calculator part. You could have used the graphing calculator to help you with graphing that inequality. But in order to do that, you would have had to have first solved your equation for your boundary line for y, which means you would have had to subtracted 3x from both sides and then divided everything in the equation by 2. So the slope-intercept form of the line is y equals negative 3 over 2x plus 9. So you would have to enter that into your calculator and graph it and get this answer. Now there's a couple of different graphing calculator shortcuts that would have let you test the point 0, 0, but they require a lot of extra button pushing, and honestly testing 0, 0 in your head is not that hard. Because if you go back and look at your original equation, if this is 0 and this is 0, then that whole side of the equation is going to be 0. So it's not hard to ask yourself, is 0 equal to or less than 18? And the answer, of course, is yes. So we know that given this graph, we're going to shade in this direction. Now, if you want to use the calculator to help you, take into account that this is below the line. This is going from the line down, okay? So what we do, and I'm going to demonstrate this for you, is this is the end result of getting the calculator to graph, and it will graph and shade for you. But this is what you've got to do to get the calculator to do that. You have to first solve the equation as I showed you. If you don't have the TI-84 that puts your fractions in as number over number, you need to put your fraction in parentheses. If you have the 84 that makes it look like a fraction, you don't have to. And I'm just going to zoom 6 for standard window.
Hold on 1 second. You did 18 instead of the 9?
Oh, I'm sorry. Yes, that's supposed to be 9. Thank you. I shouldn't talk and enter at the same time. Okay, so there's your graph. Now we look at 0, 0 and say, okay, is 0 less than 18? Yes. Did I go too fast for you?
Yeah, I don't know what you hit after you hit, after you had it at the y equals, what did you hit?
Okay, I went to zoom, and since I figured that it's going to be on, you know, really close to the origin, that I just chose number 6, which is the standard window, goes from -10 to 10 both directions. And if that hadn't showed me the graph, then I would have started hunting, but since that one did, then I'm happy with that one. And I know now that I need to shade below the line, so this is the last step. Here's what you actually have to do to get that little symbol there. You move your arrow to the left, and this is actually on your handout. You move your arrow to the left until you're sitting in front of Y1. And notice that the line in front of Y1 starts flashing. If you hit enter repeatedly, it'll change through several different things. The first one is just a heavier line. And that would be useful if you're looking at 2 lines and trying to decide which one is which. But that's no interest to us here. So then the next thing it does is it shows flashing above the line, which means you would want to shade above the line, and that's not what we want. So we hit enter again, and it goes to the part where you shade below the line. At that point, if you hit enter, it keeps on going through the different things. So you want to pick the one that has it flashing below the line and then move away from sitting on that symbol. Just press your right arrow and get off of it. Okay? And hit graph. And it will indeed shade. But I don't know if it's worth going through all of that.
No, because, I mean, if we're already choosing which side.
Yeah, if you already have
Why
to
do you
choose the
need
test
that?
point, why do you need to get the calculator to show you? Now, it might be useful to be able to check out your X and Y intercepts, I don't know, but I'm going to show you that you can graph on the calculator.
You pick what side.
Yeah, you pick what side anyway, you still have to test your point.
Yeah.
So, you know, if you want to do this, you can, but you don't have to.
Well, I guess it looks pretty.
Yeah, it looks pretty. I don't want to deprive you of being able to use the calculator if you want to. However, on this particular set of work, I don't think it's useful like it was back in doing matrices.
Understood.
Okay. So here's the summary of the steps. Draw the graph as a boundary line. Make sure the line is solid if the inequality involves equal to or less than or equal to or greater than. Make the line dashed if the inequality is either less than or greater than. Then you decide which half plane to shade because it divides it basically, your line divides your graph in half. So you decide which half to shade by choosing a test point. Now, this one says solve it for y and shade above if the inequality is of the form greater than or equal to or greater than, and below if it's equal to or less than. I don't recommend part A because we're not going to go through about, okay, when do I flip the sign over when I divide on both sides? That's too much stuff to memorize. It's much easier to use the test point. So I recommend part B. So choose step 2B. Choose any point not on the line as a test point. Shade the half plane that includes the test point if it satisfies the original inequality, and otherwise shade the other side of the boundary line. So it's pretty cut and dried. Now the next thing we're going to do is graph a system, meaning more than one linear inequality. And it works pretty much the same way. First thing we're going to do is we're going to graph the boundary of the first system, which would be y equals negative 3x plus 12. And because the symbol is going to be less than, then we're going to use a dashed line. And we're going to shade below the line because 0 is less than 12. Because if this is 0 and that's 0 is less than 12. So 0 is less than 12 is true, so we're going to shade toward the origin. Okay? Then we're going to graph the line x is less than 2y, but we're going to have to change it around and solve it for y. So x, it turns out that y is greater than 1/2 x, or y equals 1/2 x. And we're going to again test the point 0, 0, which is going to come out with 0 is less than 0. We're going to have a little bit of a problem because 0 is not less than 0, but it's not greater than 0 either. So that means we can't test 0, 0 because 0, 0 is actually on the boundary. So we're going to see what we do when that happens. So ultimately, this is where we're going to wind up. But I'm going to walk you through the steps of how we're going to get to this. Okay? So here's what we do first. We're going to graph y equals negative 3x plus 12. And since that's already in slope-intercept form, it's easier to graph that one by plotting its y-intercept and then using the slope to get our second point. And since I know I'm going to need to go up to about 12 on the y-axis, I'm going to put my x-axis down fairly low. So 0, 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I could also have just put it in the center and counted everything as 2's, but we'll leave that at 0, 12. And then we're going to count down 3. 1, 2, 3, and right 1. And that's our next point. And then we're going to draw the line. And because this says less than, our boundary line is going to be dashed. So this is the boundary line, y equals negative 3x plus 12. We're going to test the point 0, 0 because it's not on the line. And that tells us 0 is less than negative 3 times 0 plus 12, which means 0 is less than 12, and that's true. So we're going to shade this way. So there's the first one. And then we'll move on to the second one. X equals 2y. And right away, you're going to notice that your favorite test point, 0, 0, is going to be on that boundary line, because 0 is equal to 2 times 0. So you're not going to be able to test 0, 0. Although we do know that it's on the line now. We can pick a different value for y and figure out what x is. Let's say x is 2 times 1, let y be 1, x is going to be 2. So that's the point 2, comma 1. 1, 2, and up 1. Or you may have wanted to pick x to be a different number, or you may have wanted to be given a value to x and figure out what y is. So let's say we had chosen x to be 4 and want to find out what y is. Well, 4 equals 2y. That means y is equal to 2. So the point 4, 2 should be on that line. 1, 2, 3, 4, and up 1, 2. So here's what that line looks like. And again, we're using a dashed line because there's no equals to in that inequality. But since we can't use our favorite test point, we've got to pick another one. Anybody have a point that they would like to choose?
That's not on the line.
That's not on the line.
But
1, 1?
one on
No, it's not,
well,
because 1 doesn't equal 2. Okay, so let's choose 1, 1. That means 1 is less than 2 times 1, and 1 is less than 2. And that's true. So remember, we're talking about the purple line, not the red line. So we're going to shade toward 2, 1. Now, take into account that these are solutions to x is less than 2y, just like these are. And these are all solutions to x is less than negative 3x plus 12. But the only place this overlaps is in this area right here, where you see both purple and green. So that's actually your final solution, is this area here where this all overlapped. You wouldn't have to do any extra shading as long as you shade it to where you can see that it's overlapped. But that is the solution region right there. Okay? It's this part in this corner. The name of this region is called the feasible region, because it's the region that has all the solutions. It will be helpful in the next chapter, or the next section, although we don't have to do it here. It'll be helpful for us to know points like these in the next one, because those will be called corner points. Okay? So it'll help us, it will be helpful for us to know those intersection points. And for that reason and that reason only, it may sometimes be worth it to actually graph these on the calculator to be able to determine your intersection point if you don't want to do it algebraically. But we'll cross that bridge when we need to. Just keep in mind that the corner points are going to be important in solving these in application problems. So for a quick summary of what we just learned, we graphed negative 3x plus 12 is equal to y and made it a dashed line, tested 0, 0, and determined that we were going to shade in that direction. Then we graphed x equals 2y with a dashed line. We couldn't test 0, 0 because 0, 0 was on the line, so we tested 1, 1 and found out that it is a solution to x is less than 2y, so we shaded in that direction and found that the overlapping shading is this part right here. If you had done this on the graphing calculator, it would have looked like the part over here, only it doesn't have the colors. Although if you've got the newer TI-84 that has the color, you can actually choose different colors for your shading. So the calculator will show you the same thing. It'll show you shading in this direction. And if we had done this on the calculator, the shading for this direction here would have gone vertical rather than horizontal, so you can see the overlap. Okay? So we're going to do one more, and this one's a little bit different. We want to graph the feasible region for the system y is equal to or less than negative 2x plus 8, and x is only between negative 2 and 1. Those are the only feasible values for x for whatever reason, since this is not an application. So the way that we're going to do that is we're going to graph y equals negative 2x plus 8. We're going to go ahead and do that on paper first, before I show you the final result. So on paper, I'm first going to graph y equals negative 2x plus 8. The y-intercept is 0, 8. The slope is negative 2 over 1. So the point 0.8 is 1, 2, 3, 4, 5, 6, 7. Oh, I didn't plan very well this time. 2, 4, 6, 8. I'm going to go by 2s. And that means that when I go down 2, that's down 2. And then right 1 would give me this point right here. And then if I go down 2 more and right 1, that would give me that point. So everything does line up. And this is equal to or less than, so I can make this line solid. So this is the line y equals negative 2x plus 8. Now I could go ahead and shade. I'm not going to yet. I could go ahead and shade. But what I'm going to do before I shade is I'm going to take care of the second system, or the second part of the system, which is that x can only be restricted to being from negative 2 to positive 1. This would be x is negative 2. And that means that this where x is equal to 1. Notice they're both vertical lines. And the only values that I can use are the values that are in between those two lines. I can't use any values out here, neither one. So when I test to see which side of this to shade on, I want to stay between those two lines when I start doing my shading. And I can still test 0, 0 because it's in between there. So I'm going to test 0, 0. And 0, 0 is definitely in between, so it's a legal x value. But is it a legal value up here? So 0 is equal to or less than -2 times 0 plus 8. 0 is equal to or less than 8. That's true. So I do everything that's between these two lines, but below this part. So there's my solution area. Not everything on this side of the purple line, only the part that's in that band from -2 to 1 for x values. Now that's a little different. Does anybody have any questions on that one? And that area that I shaded in there is called the feasible region, which is the same as saying it's the solution to that system. Anybody have any questions? So I did graph it for you in the PowerPoint, but I wanted to be sure that you understood step by step why it doesn't look like what we did before.